In this video, we're going to look at triple integrals using spherical coordinates. First of all, we're going to review spherical coordinates. If you know them pretty well, you can go ahead and jump ahead to the examples. The video is marked to example one. But if you haven't seen these for a while, remember when we do spherical coordinates, we're measuring our point from the x-axis using theta, from the z-axis using phi, and then rho is our radius. So let's say if you have a point out here, it's going to have a certain radius rho, angle from the z-axis phi, and angle from the x-axis theta. That's a little bit hard to show this in 3D, but those are the basic coordinates. And remember that phi will range from 0 to pi, and that's all you need for phi because theta ranges from 0 to 2 pi. And of course, rho can be anywhere from 0 to infinity. So again, this is limited to 0 to pi because let's say if you're making a sphere, you only need to go down pi, and then you can generate the whole sphere by letting theta go from 0 to 2 pi. We'll see a little bit of this later. I'm going to introduce some shapes in spherical coordinates. You've probably already seen these, so I'm not going to spend a lot of time on this. But if you have a sphere of radius A centered at the origin, the equation in spherical coordinates will simply be rho equal A. In other words, if you have a sphere of radius 7 centered at the origin, rho equal A will be the equation that will generate this sphere. And of course you can see this because again, if you have it out at a radius A, and then let's say you have radius A up here, and then you give phi all possible values, that will generate a semicircle. But then if you allow theta to have all possible values, then it will repeat all the way around the z-axis. So that's going to be a sphere centered at the origin. Now, if we have a sphere that's not centered at the origin, but it's centered at x0, y0, z equals a, then this will be rho equal 2a cos phi. And this is similar to what you got when you had a circle in 2 dimensions and you expressed it in polar coordinates. We have a similar expression for spherical coordinates. Once again, this is a sphere. It's centered at A, but also the radius will end up being A. As you can see here, it's centered at 0, 0, A, and then obviously the radius is going to be A as well because the distance from here to here is going to be A. So the radius in this case is equal to A. Now, for a cone in spherical coordinates, again, let's say this angle B here is maybe pi over 4 or pi over 3. Then if you generate that angle and then allow all possible values of rho, that'll extend out forever, and then all possible values of theta, that will repeat this angle all around the z-axis. That will generate the cone. So if you have a cone, that's going to be represented by phi equal b, and where b is whatever this angle is. So we're going to use these when we calculate triple integrals. Now, when we convert to spherical coordinates, we're going to have some conversion factors, just like we did for polar and cylindrical coordinates. There we had like x equal r cos theta, y equal r sine theta, etc. And for spherical coordinates, we're going to have these conversions. One is going to be rho sine phi cos theta. So that's what x is going to be. Y is going to be rho sine phi sine theta. And z is going to be rho cos phi. And actually, if you were to take x squared plus y squared plus z squared and reduce it, do all the trig identities, you would end up getting x squared, y squared, z squared is rho squared like this. And these should be memorized, and they're pretty easy to memorize. So you're going to have rho in all three cases. You'll have phi right here, and it'll just be sine, sine, then cosine. And then for theta, it's cosine and sine. So these are relatively easy to remember, and you're going to use these a lot whenever you convert to spherical coordinates. We're also going to need the Jacobian, which is rho squared sine phi, just as when you had polar coordinates or cylindrical coordinates, you had to have the Jacobian, which was just r. So for conversion to spherical coordinates, it's going to be this. And you always have to have that in your integrand whenever you convert to spherical coordinates. So let's take a look at this problem. We're asked to evaluate this triple integral x squared plus y squared plus z squared to the 7/2, and we're integrating over the unit ball. X squared plus y squared plus z squared is 36. Now, obviously, this is a sphere centered at the origin of radius 6, because this is the same as 6 squared. So you can maybe sketch that in real lightly, or if you have a template, you can maybe do that a little bit neater. So we have this unit ball here. And now if we want to integrate over the unit ball, again, remember to generate this whole ball, we can go from rho equals 0 to rho equals 6. And then to generate, say, this semicircle, it will go from 0 to pi on phi, because remember, phi is measured from the positive z-axis. So to generate that semicircle, we get that. Then to generate the whole ball, we can make theta go from 0 to 2 pi. That'll cause this semicircle to repeat itself all around the x-axis, like this. And then, of course, if we want to substitute, remember, we can substitute up here x squared plus y squared plus z squared is rho squared. We're going to need that for our conversion to spherical coordinates. Now, there's no x's or y's or z's just sitting out there by themselves. So this is going to be the only conversion we're actually going to need. And so let's substitute into our integral. Again, for this, we're going to put rho squared, and that'll be to the 7/2 power. And again, we always have to have our Jacobian, which is rho squared sine phi. And let's go from d rho, d theta, d phi. And again, if we're starting with rho, because our radius is 6, rho is going to go from 0 to 6. Theta is going to go from 0 to 2 pi. And phi is going to go from 0 to pi, like this. And of course, we can simplify this a bit. This, the 2's will cancel. That'll be rho to the 7th times rho squared. So we add the exponents. And that'll be rho to the 9th. Now we'll integrate with respect to rho. That's going to give us rho to the 10th divided by 10 sine phi. Now put the bounds in. This would be 6 to the 10th divided by 10 sine phi d theta d phi like this. And now we'll integrate with respect to theta. And when we do that, you can see that's just going to give you just theta from 0 to 2 pi. So I'll sort of skip that step. So we'll get theta back here, and then 0 to 2 pi. So I'll go ahead and put those bounds in, 0 to 2 pi, which is just going to end up being 2 pi here. Then finally, we'll integrate with respect to phi. And of course, if we integrate sine phi, that's going to give us what? Negative cos phi. And let me bring this 2 out front here. Actually, I'm going to cancel the 2 with the 10. So it'll give us 5. And put phi, that here. Again, integrate this, you get a negative cos. Like this. And put in the bounds. That'll be cos pi minus cos 0. And of course, if you think of cosine, it's going to go like this. So at 0, this is going to be 1. Excuse me, at 1 here. And then at negative, at pi, it'll be negative 1. So we'll end up like with negative 1 minus 1. So it'll be a negative 2. So negative 2 and the negative here will cancel. So we have 2 6 to the 10th over 5 pi like that. That's our answer. So this is a pretty simple problem, although this would have been extremely difficult, very horrendous even, if we were to try to do this in Cartesian coordinates. But by switching to spherical, we were able to make everything for a sphere real nicely using spherical coordinates, and it made this integral very, very simple. Let's take a look at this problem. Evaluate this triple integral x squared z dv, where E lies between the spheres x squared y squared z squared is 1 and x squared y squared z squared is 9, and above the cone phi equal pi over 3. Obviously, this is a sphere of radius 1. And remember, in spherical coordinates, we can just write that as rho equal 1. And this is a sphere of radius 3, because this is like 3 squared. And then the cone is pi over 3. Remember, we can describe a cone by just calling the angle phi what it is. So in other words, that's going to be something like this. So where phi is pi over 3, but then since there's no rho, that means this radius will go on forever. There's no theta, so it'll take on all values of theta, which means theta to 2 pi, which means this is going to repeat itself for every value of theta. So we're going to end up generating a cone, something this is pretty rough, but that's the idea. And then we're going to have a sphere of radius 1 and a sphere of radius 3. I'll maybe just make a couple of general spheres. So let's say something that'll fit on the page. So we're going to have a sphere like this, and a sphere much bigger like this. And again, those are going to be spheres, so it's going to be like one inside the other. So these are actually going to be three-dimensional, but it's a little bit hard to show them without interfering with our cone. So I'm going to leave this open so we can kind of just see inside. But actually, there would be a sphere covering all of this going all the way around. So we're going to have to find the bounds on this. And so if you imagine, say, putting, say, a radius in the positive rho direction, the radii would go like this. So in other words, if you imagine taking rho from 0 and making a bunch of arrows in a positive rho direction, you can see that the arrows are going to start down here at rho equal 1, which is the inner sphere, and they're going to end up here at rho equals 3. And also you can see clearly a phi would go from 0 to pi over 3 because it's going to cover this area here. And theta is going to go from 0 to 2 pi. So it wants the volume in this region here, but above the sphere. So it's going to be this volume right here. And so when we make our triple integral, and we'll just set it up for now. So we'll have something this, Again, we want to convert this to spherical coordinates. And what is that going to be? That's going to be x, remember, is rho sine phi cos theta, but we're squaring it, so those will all be squared. And z, remember, that's rho cos phi, like this. And again, we're squaring those, so we get something like that. So this is x squared, z squared. And then always remember your Jacobian, which is rho squared sine phi. And let's say, let me do rho first. Again, we're going from this inner sphere to the outer one. And we're going from phi 0 to phi pi over 3. And we're going from theta equals 0 to theta 2 pi. And again, we're doing rho phi theta. That. We won't take the time to do the integral. It's not going to be real difficult because we can put all the rows together. We'll get rho to the sixth, and we can put the phis together. We'll have to do some trig before we integrate, but we can do this. But again, always remember when you do these conversions to spherical coordinates, you always have to have the Jacobian here. It's easy to forget that, but it's a very important part. And again, get your volume. You want the volume in here between the spheres, but above the cone. In other words, if it just said between the spheres, it would be all the way around. Or if it was below the cone, it would have been like, say, just this region here, but it said above the cone. So it's going to be above the cone between the spheres. And it's going to be rho from 1 to 3, phi from 0 to pi over 3, theta from 0 to 2 pi. Consider this problem. Evaluate this triple integral x y squared z dv, where E is the volume above the cone, phi equal pi over 4, and below the sphere, rho equals 8 cos phi. So let's take a look at this. Now, we said earlier that this is, again, the form of a sphere. Now, we're going to have to rewrite that a little bit. We're going to have that written as 2 something. Remember, write it in this form. And whatever is here gives you the radius of the sphere. And so the radius is 4. And again, the cone is pi over 4. So let's go ahead and draw this. So we're going to have a cone like this. And again, the sphere is inside. I'm not going to try to draw everything, with the curved lines here, but it wants above this cone and below the sphere. Again, remember the sphere is rho equal 2 times 4 cosine, or the way they give it. like this. And so that's the region we want. We want this region mainly like right in here. If you can see that shading, we want what's right in here. So now again, when we set up this integral, it's helpful to put arrows in the positive row direction. Let's say we want to do row first. Put arrows in the positive row direction, similar to what we did in the last problem, but here it's even more important. That kind of helps us to see what's going on. So if we put arrows in the region we're interested in, the volume we're interested in the positive row direction, like that, and you can see the arrows are starting at row equals 0, and they're ending on that sphere, row equal 8 cos phi. So that takes care of row. The next thing we'll want to do phi. Again, phi is going from 0 to pi over 4. And theta is going to be going all the way around. So it's going to be theta equals 0 to theta equals 2 pi. Again, make our substitutions. Remember, x is rho sine phi cos theta. Y is rho sine phi sine theta. Z is rho cos phi. And then, of course, the Jacobian, rho squared sine phi d rho d phi d theta. Just barely fit everything in. And again, let's try to simplify this a bit. Oh, excuse me, there should be a couple of squares here. So we had like x sine phi cos theta. Y was sine phi sine theta. And z was rho cos phi. But we had to square the y terms. And then the Jacobian, again, remember, always remember, have to put the Jacobian in. And d rho, d phi, d theta. And so let's see how many rows. Let's see. 1, 3, 4, 6. Row to the 6th. And then let's see. We have sine phi. Let's see. 2. Looks like 3 of those. Excuse me. 1, 2, 4 of those. Cos phi. And let's see, we have a cos theta and a sine theta, d rho, d phi, d theta, like that. And right now we're just focused on setting up the integrals, not going through the mechanics. Though this one would be, I think, a little bit of a challenge because we have, well, not really. We'll again integrate this with respect to rho, get rho to the seventh over seven. When you substitute here, that's going to give us cos to the seventh. So we'll have that here and that here. We'll have to do some trig substitutions here, and then you do u substitutions. When we get to integrating theta, we're going to just use u substitution there. It's going to take a little while, but it's pretty straightforward. Again, the most important thing is to set up the integral.